Good afternoon, everyone, and welcome to today's CPD session on microsecondary radar for drone autonomy and navigation by Cambridge Sensoriis. We're delighted to welcome them here today, and in a moment I will hand over to Steve Clark. I just wanted to let everyone know a little bit more about the ARPAS-UK CPD sessions. They are a combination of more practical day-to-day information as well as future-facing, which is rather more this side of things today. If you're interested in taking part, or if there is a topic you would like to know more about, please do get in touch with us. The email to use would be membership@arpas.uk, and we are very happy to take suggestions and actually appreciate that because it reflects what people are interested in directly. So today's session, Steve Clark, Dr. Steve Clark, is the founder and CEO of Cambridge Sensoriis. He earned his bachelor's degree in electronic engineering and physics at Loughborough University and his PhD at the Australian Centre for Field Robotics at the University of Sydney. He has over 25 years experience as a founder and entrepreneur in radar technology for industrial automation. Steve co-founded Navtech Radar from 1999, where he designed and manufactured radar solutions for the security, industrial automation, and traffic safety markets. World-first systems include radar navigation for autonomous straddle carriers at Australian container ports, radar for tunnel and motorway stop-to-vehicle detection in the UK and internationally, and radar on autonomous iron ore bulk carrier trains for obstacle avoidance. Steve is now designing all-weather micro radar systems at Sensoriis to support autonomy and BV loss flight for commercial drone services. So, Steve, I am going to hand over to you and turn off my camera and mute myself while we listen. Thank you very much indeed.
Thank you, Eleanor, for that introduction. That was quite a long introduction. I hope participants are still with us and we can get into something more relevant for this audience, talking about drones. So let me just navigate the share bits and pieces, and you should be able to see my screen now. Great. Yeah, so as you said, I've been working with radar for a number of years now on various applications, and within this business, we're focusing very much on using radars on drones, and I hope in this presentation to answer the why would you want to do that question. So when people think of radar, usually they tend to think of the large primary radar systems they've perhaps seen when they've been to an airport on the top right there. There's other large radar systems there, a surface movement radar system, also at an airport, detecting and tracking things moving around the ground, mostly aircraft. Radars on boats to detect other boats for purpose of collision avoidance in poor weather. And the one top left is a bit more interesting, and it's a missile defense radar system, big military installation. But not all radars are created equal, and there are a number of smaller radar systems that are in use as well. So people may not be aware that radars are widely used on vehicles on the ground to support driver assistance. On the top left there is a so-called advanced driver assistance radar that is designed to detect objects in front of the car and support emergency braking. It's necessarily small, somewhat lightweight, and reasonably priced to not overly impact the price of the car. The top right is a small radar system used on a runway to detect debris. So if you think of the debris that was the cause of a Concorde disaster at Charles de Gaulle Airport in 2000, radars are now available to detect just that sort of hazard on the runway. The bottom right is a radar system I worked on. That's detecting vehicles traveling along a highway. It's actually a mechanically scanned system, and designed to see if vehicles stop and alert a control room so that the lane can be closed on smart motorways. And the bottom left is a more advanced so-called 4D radar, measuring 4 dimensions. Azimuth, elevation, range, and velocity. These are the latest generation of ADAS radars. So radars can be large and small as well. So this slide says a little bit about how different types of radar work. You get a pulsed radar. They're typically used for long-range detection of large objects. You're not too concerned where the object is, within a few meters or tens of meters, several tens of meters, and they generate a pulse of energy, which is transmitted out from a transmitter antenna on the radar. It bounces off a thing, in this case an airplane, and back to a receive antenna. And the distance to the object it's reflected off is determined by the time taken for the pulse to return. The angle of the object, so rest radar measures range and bearing, is determined by the direction that the radar antenna was pointing at a moment in time. Now, all radar work very well in poor weather conditions, day or night, and the radars you saw in my first slide was certainly designed to detect things far away. The shorter range radars usually use a different approach to detect things accurately at short range. You would need a very narrow pulse and to be able to get high resolution range measurements. So there's a technique in radar called FMCW, frequency modulated carrier wave, where the transmit signal is modulated or chirped in frequency over time. The energy leaves the radar, bounces off the thing, in this case a green racing car, comes back to the radar receive antenna, and instead of measuring the time, you mix the transmit and receive signals, and you get a frequency, you get a beat frequency, a frequency difference. And then with some mathematical transforms, a Fourier transform, you can sample the data, conduct a Fourier transform, and then the frequency difference between transmit and receive tells you how far away the thing is. So they transmit much lower power. They're good for detecting at the radar and far away, and they're the most commonly used type of radar for short range devices. Now, why would you want to use a radar on a drone? Well, we have been working on use cases with sufficiently small weight and power radar to support missions like this, where you're traveling next to a power line, perhaps for an inspection, and you want to be really sure you're not going to collide with wires or pylons, or perhaps other things that are flying in the vicinity. So for detection of obstacles and avoidance maneuvers, we've developed radar systems that support that. And similarly for other long linear surveys, as they're called, if you're inspecting railway lines, the structure around them, you want to avoid the power lines, but also trees and other flying objects, particularly as missions become EV loss and ultimately BV loss. Second slide and last slide, you may be pleased to know about how radar work. I just want to mention there's two different types of radar that we're interested in. One is a primary radar, which is a more traditional type that is transmitting a signal. The signal goes out, bounces off a thing, in this case an aeroplane, and returns back to the antenna. And in this case, the the aeroplane is not cooperating in any sense. It's not particularly trying to be seen, but the radar energy will bounce off the aeroplane and come back, and you can determine where it is in the sky. Radar signals will equally well bounce off people or cars. Common misconception that it has to be a large metal object. That's not the case. All sorts of things will reflect radar energy, even a person with not carrying any metallic material. So that's a primary radar. You also get a secondary radar, which transmits a signal to the airplane. But in this case, the airplane has a transponder, detects the secondary transmission from the ground, and returns information back to the transmitter. Now, in most air traffic situations, the primary radar and a secondary radar have different antennas, operate in different frequency bands. The secondary radar in this case would typically send information back to the ground, including perhaps a call sign, flight designation, and possibly altitude as well, if that's from onboard systems. So that information can be part of the display to the air traffic controller. You see on the picture on the back, the primary radar has one big antenna. That's this one. As a secondary radar antenna array, which is coupled to it. So yes, we've talked about how radars work with pulsed radar, FMCW radar. We've now talked a little bit about primary radar, secondary radar. Let's get to talking about drones. So something we've done well, a few things we've done. We've made primary and secondary radar, which are much smaller than the larger systems you've seen. And we've used these in for drone applications in two scenarios. We've had a primary radar, which you can see on the front here. There's also a router and a battery, but the primary radar is on the front here. It's detecting things in the sky, drones that are flying. They don't particularly want to be detected. But we've also created a secondary radar that can be installed onto the drone, and we can then know where that flying drone is. It's cooperating, and it sends information back to the primary. So our system, both radars operate in the same band with the same hardware, just different software. And this is important because you can use one single piece of low weight hardware on the ground or on the drone for two purposes. On the right hand side, we've used a primary radar on the aircraft and secondary radars on the ground. In this case, we had radars on this trailer, which was being towed across the field. Some more videos of that later. And this system allowed the aircraft or the drone to locate the trailer and ultimately use it for supporting landing. It can get a bit confusing in this situation, which is the primary and which is secondary. So we talk about the primary radar as the one where the data is. The secondary radars are just powered. They collaborate along with the primary, but the data feed, the API, comes from our primary radar. So a couple of use cases of that technology. Radar on a drone to support on a vessel, support landing on a vessel underway. If you have secondary radar, which only weigh a few hundred grams on the vessel, you can locate them. And the drone can not only know where the vessel is, it can relative to itself in 3 dimensions. It can also measure something about the vessel, like what's its heading relative to the drone and how is the deck moving to support landing when the sea state is considerably more rough than it is here. The same hardware can be used to avoid obstacles as you come into land, or indeed as the drone has gone off to complete a mission, in this case perhaps to inspect turbine blades on a wind farm, and to, of course, not impact the blades during the survey. Another use case is to support resupply of people on the ground. Radars on the drone, collaborating with radars on the ground, allow the drone to come in relative to these guys without GPS and just measuring relative to position to the endpoint, not absolute world coordinate positions. And finally, radar surveying vertiports. concept picture here, because eVTOLs are still concepts, and sending information via radar directly back to the ground. So that's an overview of a bit about how radar works, some of the markets we think our technology is useful for in this space, and that leads to 3 slides on product. So what's come about out of our activity over the last few years in this sector, and we've created 3 products. One is radar aware. So this is a radar that goes on a drone and allows you to detect other obstacles round and about and report them to the flight controller. So if you're surveying power lines, you can detect those and locate them relative to the drone. Other drones that are flying, or buildings in a urban mission. And there's we started this work in some flight trials under Future Flight Challenge Phase 2, 2021, middle 2021. We're continuing that now in Phase 3, and very soon we'll be releasing this RA1000, which has got detection performance as you see on the screen there, and an API and swap size, weight, and power in the region of 500 grams. So that's product 1. Product 2 is the ARC locate. We've got radar aware, we've got ARC, and a radar on a drone to get to an endpoint without GPS, without radio communication from these guys to control the drone in. Very low power transmission, very difficult to detect, but the radar can locate itself relative to the endpoint over hundreds and hundreds of meters. And we'll be extending that all the time. The next release will target 1,000 meters detection range. And you saw a bit of this in a previous slide, the ARC landing. So that's a radar collaborating with other radar on a deck, or either moving or stationary, to make sure that the drone has the relative position of it to the landing point. Each radar point will give you range, bearing, and elevation, and together you can use that information to locate this guy very accurately and determine the heading and other movements, other degrees of freedom of this vessel. So radar aware, ARC locate, and ARC landing. Here's some of the hardware we've got. We've got an IP67 housing that would go on the deck typically, low ingress protection housing here for drone use, but also lower weight. That weighs a little over 100 grams, or an OEM board, which weighs approximately 30 grams, which can be incorporated into a drone, has very little impact at that weight. It draws about 5 watts of power. So we're making these. They're available, and yeah, we took them to market first at DroneX towards the end of last year, and yeah, lots of interest in that ARC capability. These are suggestions on how it can be deployed with 3 on the ground. You can, as I say, you can locate the drone, but you can also say something about how the vessel is moving, what's happening to the deck, and control the landing. Or equally, you could, in a fixed landing zone, you could have 1 ARC on the drone and just 1 on the ground, measuring range within 1 centimetre and the angular degrees of freedom within 5 degrees, and improving all the time in that area. These slides show some work we've done flying radars, testing, coming into land at the bottom there on a fixed location, and at the top onto a moving location, sending information to a mission computer on the drone. We have measured the position of the drone relative to the secondary radars on the trailer as it's being flown. You can see the video running there, and which has been flown manually, but taking the radar data and measuring as the drone comes into land on that trailer. You can see there's quite a lot of vibration on the secondary radar, just the bottom right of the image there. But that doesn't matter. The radar measurement is still resilient, and yeah, with 1 centimetre accuracy from drone to trailer radar. We've combined some of that information to sort of multilaterator position in this video. This was taken at our office in the early days of testing, with 1 centimetre accuracy on each of the distances to these other radar on the ground. Each of the radar has its own unique ID. You put them all next together and on top of each other, they can't be confused. They don't interfere, and they are unique. And the system supports multiple IDs. Here we're showing 3, and locating the drone as it's moved close into the secondary radar. And then turning things round. So in this situation, we had a primary on the ground, secondary on a drone. A little bit difficult to see there, but the drone has an ID. So you know, because now the secondary radar on the drone is cooperating with that on the ground, and you know which drone is coming into land because it's announcing itself, its identifier, and making itself conspicuous to the primary radar on the ground. So yeah, I think we're pretty much at the end. One final slide. We've got demonstration equipment. We've shown this at trade shows. There's a radar here and other radars on the ground. We can quote unquote fly this by carrying it around, and there's a screen which shows the position of this relative to these. And we run demonstrations all the time at our offices in Cambridge. There's actually radars permanently installed on the side of our building, and we fly around this primary radar and locate it and show it to customers. And that is, I think you'll hopefully agree, a whistle-stop tour of how the radar work and how we've applied some neat technology to support drone obstacle detection, navigation, and autonomy. Happy to take any questions, but please also connect with us on LinkedIn, tweet us, yeah, from me, that's it. Thank you for your time.
Steve, thank you very much indeed. As you say, that was a whistle-stop tour of radar, but that was fascinating. Thank you. And there are some definite use cases, and there is huge potential there for the industry, particularly as we start venturing into the BV loss side of things. And it's good to know that the technology that is there and ready to be able to support such operations. It's highly encouraging. Are there any questions to start with? We will please use the Q&A box. I'm going to kick things off. I think was a question that I had, which is why choose radar specifically, for instance, over on drones, over other cameras or other sensor payload side of things?
Yeah, I mean, the great thing about radar is it's a long-range, accurate detector that will work in all weather conditions, and that's pretty much indisputable. Radar are widely used on detecting aircraft in the sky in an air traffic control scenario, because they work in all weather, day or night. They're widely used on cars for emergency braking and obstacle detection. And what we've done is made them smaller and lighter and tailored them for use on drones. Compared to cameras, there's all the visibility issues I've mentioned, but they also measure range. You know, a camera doesn't measure a range. I'm not suggesting we should throw away all our cameras, but it definitely brings a different aspect to the measurement, a capability which can't really be achieved with other sensors solely.
Yeah, absolutely. Okay, that's an excellent answer, and totally answers my question. So thank you. That was very informative. Do we have other questions at all at the moment? Please do feel free, because this is the ideal opportunity to ask any.
Yeah, I wanted to ask Steve if you can you elaborate on the default silent technology that obviously exists within ARC? Obviously, it's a great use case within security and defense, but what is that? How does that work, and what does that offer?
Yeah, so often some of our customers want the radar technology on a vessel to be default silent. So they don't, I mean, the radars transmit very little power. It's just milliwatts of power, but they're concerned even about that. So they don't want the vessel, and these aren't civilian applications usually, they don't want the vessel to be transmitting. So it could be announcing where it is. So our technology ensures that the radars on the vessel only transmit once they've detected the compatible ARC on the drone. And therefore they're not usually announcing themselves. They tailor the amount of power they can transmit, so it's just enough to get to the ARC in the air, and so it's very difficult to detect that transmission from the boat because of this sort of default silence capability which we've baked in.
Yeah, thanks.
Okay.
So do we have any questions at all at the moment? Otherwise I will assume that everyone knows everything and is up to date with everything there. I will ensure that the session is sent out later on this afternoon with the watch again links to everyone, because I know there are a few people always who aren't able to make the session in live. So we will make sure that everyone has these details afterwards, along with contact details for Steve and Gareth. We've got a question here. It's, what is the Ofcom view of having multiple radar in flight over UK?
Yeah.
Thousands of radars.
Yeah, that you've got to be, I mean, it's a transmitting device, so you've got to be mindful of what Ofcom's regulations are in the area, and there are certain bands you can use on the ground, so and in the air, and these are things we're mindful of. So we make sure that we transmit in bands, and it's not just the frequency; it's the sort of power levels and antenna gains and all sorts of things that Ofcom allow. In some areas, the specs aren't well developed for, in some cases they are, but in some cases they aren't, particularly for longer range requirements. And, you know, the technology develops hand in hand with the regulations. You can't regulate something before it exists, usually. So yeah, we've got active dialogue with Ofcom and other regulators about the band, and yeah, some of our technology we don't need to talk because it's fine. Others, there's things we want to do which we have to talk to regulators about. So yeah, good question. Thank you.
Thank you. Thank you indeed, Jeremy. Yes, indeed, there was an Ofcom consultation on drone licenses recently, wasn't there?
Yeah, that's very helpful. Yeah.
So I think we may be done for the day, unless anybody else wants to come forward with questions.
I think my presentation was so good that
indeed, I think it was flawless. I think it answered everyone's questions, but it was ideal.
All right.
Okay, well, thank you very much, everyone. And we will, as I say, I promised, we will get this information out to everyone this afternoon. And please do get in touch if we can't, if you can't get through to Steve and Gareth, please do come via ARPAS-UK, and we're more than happy to forward on messages to them. We've had a comment saying, great presentation, and we'll follow up afterwards as well. So thank you very much indeed, Steve and Gareth, today. And we look forward to hearing more. Okay.
Thank you.
Thank you, everyone.
Thank you. Bye-bye.
Enjoy the rest of the day. Bye-bye.